to begin, and we'll get to section 5.1 today. We're going to begin talking about energy. Okay, and specifically, today we're going to talk about work and energy. Work and energy. Now, we'll go into the objectives. But somebody tell me in your own words, what does energy mean, or what does work mean? Energy, work. Where have you heard the term? Paul.
Energy is like the amount of force to do work.
Okay, you're close. You're on the right track. Because force is involved in energy, for sure. Okay, a form of energy could be like something in terms of electricity or heat energy, like thermal energy. So there are many categories of energy. Categories. Where have you heard energy before in like physical science? What types of energy have you heard of? There are mainly two types. Static or potential, same thing. Very good. So there's kinetic and then there's potential energies. And we're also going to talk about work. So here's what I mean by work. Work is whenever you exert energy. Okay? Work is literally, if you exert energy, you do work. So for example, if I want to move this book across the table, I have to do some sort of work. I'm exerting energy to move it. If I want to walk up a certain amount of stairs, I do work. I have to take a step every single time. So whenever there's work done, there is energy involved. And we're going to learn in section 5.2 about the work kinetic energy theorem and how they're related to each other. Today, specifically, what we're going to start is looking at work itself. All right? Any questions? So again, we're going to define and understand work, identify when work is actually being performed, and calculate the net work as a result of several forces. All right, so by definition, here's what work actually is, scientific work. It is the product, and we'll go through all this one step at a time so don't get overwhelmed. It is the product of the component of a force along the direction of the displacement and the magnitude of that displacement. And it looks like a complicated equation, but it's actually very simple. And we'll go into the exact application of it in a minute. So again, it is the product of the component of a force. Component, that's where the cosine comes in. Whenever you see a cosine or a sine, you're looking at components. Along the direction of the displacement and the magnitude of that displacement. Magnitude meaning absolute value, that's why you see the absolute value around the x. Your book uses the letter D instead of absolute value of x, which is fine, because D stands for distance. And if you know that the displacement is, say, 10 meters, then the distance is 10 meters. Even if the displacement is negative 10 meters. The distance is still 10 meters. So the absolute value is the way I like to write it, so I remember what's going on. Okay? Now, F net is the overall sum of the forces, and cosine theta is the cosine of the angle between the applied force and the actual motion of the object. And that's the tough part I'm going to explain now. So before we get into the next part, we don't have to write anything else down. Let's just look at a quick free-body diagram. Let's say this object is moving to the right. So it's moving from left to right, and there's a force acting on it. The force acting on it is where F net comes into play. The actual displacement is where the x is going to come into play. But the question becomes, where is theta in this example? Where is theta? And here's how you do it. You take the directional, which is to the right, right? The direction of this movement is to the right. And you draw that underneath the force, like this. Draw your x underneath the force. So whatever the directional is, draw it underneath the force. Okay? Now, the angle that it makes in between there, that's theta. That's all it is. Again, if you're moving to the right and your force is like this, then there's your angle. Now, it's possible to be having opposite directions. I could have this, imagine this desk is sliding out of control, and I want to stop it. I would have to apply force this way. Would you agree with me? Right? If this desk is coming at me, I'd have to push that way to stop it. So the directional is toward me, but I'm pushing that way now. So you could have something like this, where the directional is to the right, while there's an applied force acting to the left. Well, now we go ahead and move our directional up. We put it over here so that it overlaps, put our directional there, and now this is theta. Again, you take your directional, slide it up so that they meet at a vertex. Focus, guys, come on. The angle that it makes between the directional x and the force being applied is the theta value. So this value of theta is no longer going to be between 0 and 90, right? Because 90 degrees would look like this. That's an angle of 90. So this angle is obtuse, clearly. An obtuse angle is between what values?
Between
90 and
180.
90 and 180. Derek.
That diagram you drew, is that if the desk was sliding out of control and you stopped it?
Correct. So imagine the desk was sliding out of control.
Why is the force that you're pulling it from?
Yeah, so imagine it's sliding out of control that way, and I take a harness and I hook onto it and I pull back to stop. Or I stand on this side and I push. Then this force would just be on this side now. You would still have the same angle.
But if you pulled directly.
If I pulled with the
horizontally
motion or against
against
it,
it,
it's still.
I'm saying, like, why is it diagonal? Why is the force diagonal?
Oh, because I was pulling at an angle, but I could pull directly against the carrot like this.
It'd be 180.
Yeah, that's what I was getting into in the next slide. That's what I was doing. I was leaving. But yeah, imagine you have a force to the left. Now your directional looks like this, and then the angle is just 180 degrees. Yep.
Wait, so the direction of where the force is coming from is based on the angle?
What do you mean?
Like, so in those two, the angle is smaller, so does that mean, so the one on the right, there's a smaller angle, so does that mean there's less force?
No, that's a very good question, Paul. And then the reason that it might be a little bit not clear is because you haven't studied, remember, the rest of the trig that we were talking about? So I'll explain now what happens here. So, before you ask your question, one thing to notice, if you take the cosine of an angle, and you should write this down because you don't have this written down or in knowledge yet unless you've taken trig, aside from school. If the cosine of theta, if theta is between 0 and 90, is a positive value. If theta, again, if theta is between 0 and 90, it is a positive value. But the minute theta is between 90 all the way to 270, which we're not going to get to, but say you went all the way to 270, any theta value between 90 and 270 is negative when you take the cosine of it.
How does that make sense?
Okay? To explain it, Max, and I'm not saying I don't want to explain it because it's very easy to explain, but it would take me about 10, 15 minutes to go with everything. And I can't right now. So for now, until you learn it in Algebra 2, just take it on faith. Okay? The cosine of an angle is less than 0, or it's negative, when the angle is between 90 and 270. So in this case here, if theta was like, say this is, I don't know, 150, the cosine of 150 is going to be negative 0.866. Okay? You don't need to memorize that, but I'm just giving you an example of that. Okay, that's what it would be, a negative quantity, a negative value. So, what that means really is that work can be negative or positive. Think about that for a second, right? If your cosine of an angle happens to be negative, in our equation we're going to have a force, which is positive. We're going to have a negative value from the cosine, and then a positive value here. So if this were to happen, we're going to have positive, negative, positive, which would give us a negative overall work. A negative overall work.
On that 3-body diagram, why is it the force is going left diagonally, but you're pushing to the right?
You're not pushing it. This is an example where the object is already in motion to the right, and you're trying to slow it down. So say it's sliding uncontrollably, and you're able to lasso the object and pull it backward. It's still moving that way, but you're applying a force to slow it down. And it might drag you for a little while, but you're still applying a force. It's like a tug of war. Okay? So the motion of the entire team might be moving forward because your team is losing. But which way is your force being applied? Backward. So the work there would be negative. Okay? It's a good question. Now, let's look at our units real quick. The units of work, force, measured in newtons. Cosine of an angle has no units at all, it's cosine. X is measured in meters. A newton times a meter is called a joule. Another unit you should have memorized this year. Joule. So a Newton times a meter is a joule. And you're going to hear that. You're going to also hear that when we study kinetic energy and potential energy. They're measured in joules. It's a measurement of energy. Energy. Okay? Work is measured in joules. Work is measured in joules. Work is measured in joules. What is work measured in?
Joules.
All right, let's look at the next slide. We're all good on this one? Example. How much work is done on a shopping cart when it is pulled 12 meters by a force of 75 newtons at an angle of 60 degrees? And I'm telling you guys now, this is one of our easier chapters. So please take advantage of it. Okay? It really is. Because the math in this chapter is quite simple. It's not difficult math. For you.
Do you want us to draw a diagram?
I would draw a diagram, yeah. I would definitely draw a diagram to start.
I'm tired.
Bodygram? So now it's going to be positive. Alright? Cosine?
Again, very good. Cosine is between 0 and 90, so the work done in this example will be positive. Okay, it will be positive.
If the angle is between 0 and 90, it's positive. Okay.
Because the cosine of an angle between 0 and 90 is positive versus 90 and 180 is negative. So my formula is the net work done equals the net force times cosine of theta times the absolute value of x. Now, the net force is the overall sum of all the forces, but take a look, guys. There's only one force acting in this problem, right?
Yeah.
So I can just write this equation if I want for this one as this. Okay? Again, whenever there's just one force acting on the object, just write it like this. You don't have to go crazy and write it with net as a subscript. Jack.
That's multiplying the absolute value of x, right? Is that what you're doing there?
Yeah, it just ran out of room. Times, times, times. And there's a, oops, not times in between the theta and the cosine. No. You don't need to say that. There it is. I know, I probably should calibrate it, but it's always off anyway. Tyson.
Why are you playing a diagonal? Because it's a 60 degree angle.
Yeah, so 60 degrees is between, remember, the directional, which is horizontal,
Yeah.
and wherever the force is.
Okay.
So I just kind of like move up when I ask it.
Yeah, makes sense.
All right, plug in now. Easy problem, 75. Cos 60 times absolute value of x, which is 12 meters. What do I get as an answer?
12 joule. No.
I believe it's 20. I don't think so.
Check, people. Come on, let's go. Let's go. Get your calculators out.
Yeah.
It's got to be in degree mode. It's got to be in degree mode and not radian mode.
I don't think you can.
You can. You actually can do this in your head if you know what cosine 60 is.
Yeah, but yeah, Max.
You gotta
yeah,
know.
obviously.
Once you study this and recalc, cosine 60 is one of your standards. It's 1/2. This is literally just 1/2 here.
What has to be in between?
25. That's what cosine 60 is. 450. Very good. And my units are
Yeah, man.
joules.
That's weird.
Joule. Units are joules.
Molly, I did the answer too.
So 450 joules of work are performed. If you didn't get that answer, hit mode and make sure you're in degree mode and not radian mode. Radians are types of angles that you will learn about this year also in trigonometry. But radians are just like degrees. It's like meters versus feet. They're units. Radians are different units. Okay? Questions at all on this problem? Should be just plug and chug, right?
Yeah, it's easy.
Just plug it on in and going through the problem. All right, let's take a look at the next thing, please.
What's the spring?
So we have two questions here. First, what would the angle theta be if the force is is a horizontal force in the direction of the displacement. Horizontal, so no longer at an angle. What would the force be, what would the angle theta be if the force is a horizontal force in the direction of displacement, or what about in the opposite direction of displacement? Okay, in the opposite.
Going the first part, would it be 0?
Very good, Jack. Well done.
And the opposite direction would be 180?
That's exactly right. Let's go over this now. Well done, Jack. So, we've got a horizontal force, F. We've got the direction, x, acting in the same direction. That was the first scenario. The second scenario, where the directional is here still, but now the force is acting in the opposite direction. So we're looking at these two separate examples now. In the first case, here's what I do, people. I take the x vector and do this. Just put a little dashed line over it to show that's my x there. What's the angle between those lines? It's just 0. There is no angle between them. They're coinciding. As opposed to up here, if I take my x vector and do this now, and put it here, now I can see that the angle, as Garrett said before, was 180. Very good. Now, here's a fun fact for you. Go ahead and type in cosine 0 in your calculator. What do you get? And what about the cosine of 180? -1. Let's go over this and make sense of it logically. So, scenario 1. The force and displacement are both in the same direction. In the same direction. You okay?
Oh, the chair went down.
I saw it. So, the force and displacement
14-inch foot.
are in the same direction. And we have a cosine value of 0, which comes out to be +1. So when the force and the displacement are in the same direction, work is positive. Or variably, how would I write that? Work is greater than 0.
The way you were talking before doesn't make sense how it could be 0.
How theta could be 0?
How work level did.
Work is not 0.
How work be negative.
Oh,
You're putting something that's positive. So
yeah, but if the object is already in motion, and then you start opposing the motion, it's like friction. Friction is like losing energy, thus it's a negative work. When you exert friction, you lose energy. So that's where the negative comes in. Now here, if you were to take the cosine of 180, it's -1. So this work is going to be negative. So in this scenario, work is less than 0, or negative. In this scenario, work is positive. So to summarize, God bless you, to summarize, if the force and work are in the same direction, it's positive. I'm sorry, if the force and displacement are in the same direction, it's positive. If for some reason the force and the displacement are in opposite directions, it is a negative work. An example of that is friction. If an object is sliding to the right, which way does friction act? To the left. Thus you have negative work, or you're losing work, or you're losing energy. Friction is the loss of energy. That's what it is. When you rub your hands together, you're losing thermal energy. You're also creating it by doing work, but you're losing that thermal energy as an exothermic process. Remember in chemistry you learned about endothermic and exothermic? This is an exothermic process. I'm giving off heat. I'm losing energy. So that would be a negative example of work, because the friction opposes the motion.
what if the force was vertical?
What if the force was vertical? Is the displacement also vertical?
Still hold up.
I don't think that's possible. Let's see. So it's sliding horizontally,
The desk was sliding. And
Okay.
you had a rope, like maybe on a pulley.
and you start to pull it up, so the desk is sliding and pulling up at the same time. What's the angle going to be between the force and the displacement? What is it?
90.
90. What's the cosine of 90? What's the cosine of 90? What is it? 0. So is any work done? So is any work done if you're perpendicular? No work is done. Watch this guys, if you have a pulley and you're lifting something out of a well in the ground, so the displacement is upward and the force is upward, then theta is still 0, because it's like this example over here. So, I'm glad you brought that up, Derek, because we can comment on that. So, if we have an example where there's an object moving upward, and the force is also acting upward, well then theta is 0, so then we're back to having normal work. And that's moving an object up, which is gaining potential energy, which we'll talk about in the next section.
What was the first thing you said? If force and deflection
Are in the same direction, work is positive.
and they're in
Opposite direction, negative. You're welcome. We are recording. Oops. Hold on, guys. Hang on one sec. There should be, you can write that down for now, but there should be another part of this problem.
Or smarter.
They're probably much more
It's cold. It's wet.
Guys, check out Gabe. Gabe in the
Door.
I'll sit down. I'll sit down.
Guys, come on. Don't.
I got Jug.
They're
With Michael Tierney. We hid under Mr. Robbins' desk.
Wait, one time they hit under Mr. Robbins' desk and he sat down and started tickling his leg.
That's really kind of weird, guys.
He was having meetings with me in his office and he thought it was just me and him. And then all of a sudden he got a little tickle and it was Tierney and I was under his desk. Thanks.
It's how you get rid of that baseball.
Oh my God.
They've had to be serious.
If you go on Florida,
It's gonna be blast.
I tell you now,
you will have the time of your life.
I'm doing a service for the leagues during spring break. It's the same week.
That's valid.
You're lucky.
That's valid.
No, I think it's
All right, now, we have three parts to this problem. First, a student pushes a 20 Newton desk with a horizontal force, horizontal, so what's theta going to be?
Zero.
Or
Negative.
one or the other, okay? Now, with a horizontal force, a distance of 24 meters, assume the coefficient of kinetic friction between the crate and the floor is 0.2. That's mu k. Remember mu k from the other day? All right, mu k. How much work is done by the worker on the desk, the worker pushing? How much work is done by the floor on the desk? And what is the net work done in this problem? This is a little bit tricky because of the setup. The math is quite simple. The setup is tricky. So let's go through this. Let's look at part A first. It will help me a lot to think of this with a diagram. So, now, if, and by the way, this says worker. I don't know why I put worker, not student. Let's change that to student. I don't know what I was thinking. I was thinking about the word work. Yeah, it should say student. I should say student. Now, the student is pushing with a horizontal force of 12 newtons, a distance of 24 meters. So it doesn't say anything about the directions, but if the student is pushing the desk 24 meters, then the motion and the force have to be in the same direction. Again, if the student is taking this chair and pushing it 24 meters, the force is that way, and the direction is in the same way. So for this problem, we have a force of push acting this way. The direction of movement is also this way. Now, which way does friction act? Against it. So when I look at friction, what's my angle going to be when I use the friction parts?
Well, it's gonna be 180 again.
It's going to be 180, but what about the FP? What is that angle going to be?
182. Well, good, no, because kind of.
0. If I move my x directional up here and I overlap it, isn't that angle going to be 0? But if I move my x directional and overlap it with FF, the angle here, this FF angle is going to be 180. That's where this comes into play. Whereas this angle right here is 0. So when I'm looking at part A, with the work done by the student, I'm looking at the push from the student, so the theta value in part A is 0. But when I go to part B, it says how much work is done by the floor on the desk. What kind of work does the floor exert? Well, it exerts a normal force upward, yes. But what does the floor do to stop the motion? It applies friction. So the work done for part B, we're going to use a theta of 180. So you're going to see how part... Yes, because FF is what's doing the work on the floor. Again, the work done by the floor is frictional. The work done by the student is the push, the actual push.
Not including the, I forget what it's called.
Normal force and weight, or...
It takes like more force.
Oh, static force?
Yeah.
We're not looking at static, we're assuming it's already in motion.
What's
Wait,
that?
with the dotted line, it's going the opposite way?
Yeah, because if I take the x and I slide it up here, and I put the x right here, now I can see that that's 180. Whereas if I take the x and overlay it up here, the x is actually, or the theta is going to be just 0. Now, that's a good question you asked, Garrett. Garrett said, are we ignoring what it takes to overcome static friction? Well, here's my answer to that. The force needed to get this to move is very large, 1, and 2, it's not moving. So no work is being done. Remember, the definition of work is force times cosine theta times the absolute value of x. If I'm doing work, or if I'm pushing on this desk to get it moving, is there any x value right now? So the work done is just 0. So I don't care about overcoming static friction for work. Work is done when the object moves. So for part A, let's take a look at part A. For part A, we are looking at the work done by the student. What kind of a force does the student apply? How much is the value of the force? What is the value of the force that the student applies? That's the 20 Newton desk.
Oh, 12.
Guys, stop talking. The student pushes a 20 Newton desk. This is the weight of the desk, people. This is the weight of the desk. That's Fg. With a horizontal force of 12 newtons, that's Fp.
That's not
So
the
please
mass,
be
is it?
careful. Look at the units. The units say
Newton.
newtons is a weight. The mass would be in
Mass, or, grams.
kilograms or grams, either one.
What does G stand for again?
Gravitas.
Fg, the force due to gravity, the weight. The weight. So the force applied by the student is not just F, but let's put a subscript here and call it Fp. Because the student is pushing. That's the force he's applying, or she. Cosine of theta. What is theta for the student pushing? 0. That's over here on the far right of my FPD. So I do cosine of 0, which, Joey, what did you tell us before? What's the cosine of 0 equal to? 1. So does that affect the problem? No. So you can just write it, but don't worry about it. And absolute value of x is just going to be 24 meters. So that's the work done by the student on the desk. What do I get? 288?
Yeah.
Is it just 12 times 24?
Yes, because cosine of 0 is just 1. 288? Okay. Units of, what does J stand for? Joules. All right. Let's look at part B. Somebody tell me, what is my force that is acting from the floor on the desk in part B? Friction force. Very good, Masha. Friction force. So let's take a look at part B now.
Don't you do gravity for this one?
Sorry?
Don't you, like, do gravity for this one? Or
We're going to need to use that, yes, very good, because we need to calculate the force of friction. We're not given FF. We need to figure out what FF is.
do you draw another diagram?
We can use the same free body diagram. All right, let's take a look now. Part B. Work equals force of friction now, because we're looking at the work done by the ground, which is friction, times the cosine of theta times the absolute value of x. But the problem is this. You don't know FF. You know mu. Mu is 0.2. What is the definition definition of FF?
mu times Fn.
Very good, Molly, very good. So,
What was the
FF
question be again?
equals mu times Fn. So, I know mu is 0.2, but I need Fn.
Which is the Fg.
Very good, Molly, very good. Think about your y direction now.
How do we know mu?
Mu is given. It was given as 0.2.
You just pay for that.
It said at the very end of the problem, it said the coefficient of kinetic friction. Now, focus guys. Paul, up here. Let's go. We want to find Fn so we can multiply it by mu so we can get Ff. So look at the vertical direction and look at the forces. We've got Fg acting down. We've got Fn acting up. Is there any vertical motion of this object at all? So the acceleration vertically is just 0. So if I want to figure out what Fg and Fn are, I say sum of the forces in the y direction equals may, like we've been doing. The forces in the y direction, we have Fn acting up, we have Fg acting down, and that equals 0. Because there's no acceleration in the y direction, so this is just 0 here. Next, I want to figure out what Fn is. So how do I get rid of Fg? Yeah, just move it over to the other side. So by doing so, if I move Fg over to the other side, I get Fn equals Fg. Come on. If I move Fg over by adding, I get Fn is equal to Fg. So,
Sir, what does Fn have to do with the original question?
Fn comes into play right here in the force of friction. And we need to plug in, instead of Fn, what its definition is, which is Fg. And Fg is given. You're told it's 20 newtons. Isn't the desk? The beginning of the process is a 20 Newton desk. That is Fg. So Ff is mu Fn. So Ff is really mu Fg. Again, Ff is defined as mu times Fn, but since Fn is Fg, we replace the Fn up here with the Fg down here, and we can put that right into our equation.
Wait, what's Fg again? We just figured out, right?
Fg is the weight of the desk,
Right.
which is given
Yeah.
20 newtons.
Okay, got it.
And now we can just plug in, because now we know numbers. So again, this problem becomes a little bit tricky because we have to remember that we're not given the force of friction. We're not given the normal force, but we are given the weight of the desk, which happens to be the same as the normal force right here. We can take that normal force and plug it in right here to get the coefficient, or the force of friction. What's the cosine of 180, Joe? Negative 1. So this answer is going to be just a negative quantity, right? So let's go through this. 0.2 times 20 is 4 times 24.
96.
And we put a negative sign in front. We put a negative sign in front.
And it's joules.
Come on. Why do I put a negative sign in front?
Because the cos is
Good. The cosine of 180 is negative 1. So if you want to in your problem, just do this, guys. And ladies, obviously. People. Let's replace the cosine of 180 with the number negative 1.
Should we know that?
Okay?
We should know that. Like, will that come up on the test and stuff?
You'll have your calculator, so you can always use it. But it is good to know those values, yes. Guys, please don't be sure. Now, if I want to find part C says the overall net work done. If I want the net force, I would just add the forces together. I want the net work. So what can I do with my two work values that I got? Yeah, just add them together. Okay? So let's go ahead and do that. Work 1 was 288. Work 2 is negative 96. Adding those two values, 190 what? And is it positive or negative? So, if there is a positive amount of work done, it means that the student pushing overcame the force of friction. Okay? Again, the student's work is more than the work done by friction, so the object will move to the right. It will move, which we know it did. Now, there's another way to solve for work net. So I'm going to give you an alternate method. And the alternate method is to do this. Use your equation. Now, watch what happens here. If I use this equation here, F net, what was the force acting to the right? What did this person provide a force of? How many newtons? 12 newtons, right? What was the friction force acting to the left? 4. And it was, since it's acting to the left, negative. Now, cosine of theta, which force is bigger, 12 or negative 4? So the object moves to the right overall, right? So this theta is just 0 now. Again, and listen carefully. The 12, which is acting to the right, overcomes the 4 acting to the left. So theta is 0 in this problem. So this is going to be the cosine of 0, which is just positive 1, times the distance of 24 meters. Well, it's just 8 times 24, which is really just 192.
But it's a lot easier to just.
Personally, I would do it this way if I knew the works already. But if you started this problem from the beginning and you didn't solve in part A and part B, then it might be useful to use this last equation because it's quicker in one equation. Ready? Your homework tonight is going to be on Moodle, so we're going to look, but it's right here on the board already.
We have a test tomorrow.
It's not due tomorrow, obviously, but do it over the weekend for Monday.
Oh, I found something.
I had a question.
Oh, me?